Okay, so yeah, I'm Eric Severson. I'm in the electrical engine and engineering department. And as Scott said, part of the Wisconsin Electric Machines and Power Electronics Consortium. So I thought I'd start by just giving a little bit of my background because I'm kind of a recent arrival here. I did my PhD at the University of Minnesota, and my research advisor was Ned Mohan, who I never realized he was shorter than me until my commencement picture. So I'm from not very far away, but at the same time, a little bit further away, I had a co-advisor, Robert Nilsson, at the Norwegian University of Science and Technology. So I spent about a year over in Norway doing my PhD. I built all my hardware up over there. And then through a lot of trips back and forth, we finally brought it here to the U.S. and now it's actually here in Madison. I'm going to show you some pictures of it.
Is that the room in Trondheim?
It's in Trondheim, yeah. So that's our main engineering campus. Yeah. And I was hired as part of the Energy and Sustainability Thrust in the Grainger Institute for Engineering. I joined August 2017. So I like to joke that, I loaded my family up from the frozen tundras of Minneapolis and came to tropical Madison. And I kind of believed that through last fall. And then this winter, I felt like I was home again in Minneapolis. And since we've arrived, we've grown our family. So we're happy. We have a 4-month-old at home. He doesn't like to sleep all the time, but a lot of fun. And so this is I'm in the second semester of my second year here. And I've got a great team of research students here on campus, so 3 PhD students and 4 master's students. And I've got a couple of visiting scholars in my lab right now who help me do all the cool things I'm about to tell you about. And so my research group, we focus on high performance motors, magnetic levitation, and then the power electronic circuits that operate all this thing. And so we like to, Venn diagrams, we like to play in here. And if you think about the applications that this can carry over to, you can think about industrial compressors, electric turbochargers, spindle tools, flywheel energy storage. If you can rotate a shaft very efficiently, you can use it to store kinetic energy. And then most recently, we started getting into off-road vehicle electrification. There's lots of energy conservation and sustainability opportunities here. So today's talk is going to be mostly about the top left corner, which is industrial compressors, and specifically about magnetic levitation technology and how it can make real energy efficiency improvements in this space. And so it's probably not surprising to you to hear me say that electric motors are fundamental to your lives. They're involved in everything from pumping the water that you drink, to generating electricity that we use, heating and cooling our homes, our places of work, and they're all over in our electronic devices, from little fans and actuators. And so given that, it's also not surprising that they are a big consumer of electric energy. In fact, they're the single biggest consumer of electrical energy, representing about 45% of all global electricity goes through a motor in some way. And so in this space, we can talk about modest efficiency improvements to yield huge energy footprint changes in terms of sustainability. So electric motors have absolutely got to be a part of any conversation with regards to energy conservation and sustainability. And so this talk is going to be about that, making efficient motors, but a little bit more pointedly, it's going to be about motor bearings or how to get rid of motor bearings. I do not like motor bearings. So they are typically the first point of failure. This is well known. They're also a source of significant losses, especially when you go to higher and higher speed machines, and you go to higher and higher speed machines to reduce the size of machines. And perhaps a little bit less obvious is that lubricants for bearings can cause major problems with the broader system that they're connected to. And I think the first 2 points are fairly self-explanatory, but the third point perhaps can use some more motivation. And my favorite example for this is actually HVAC system. So this is a picture of the chiller on top of the WEI building here. And so when you think about systems like this, they're very large. You can also think about how every watt that you put in counts twice. So if you have a watt of inefficiency in your system, it ends up heating up your refrigerant, which is another watt that you have to pull back out of your building. And right now, HVAC represents about 17% of US energy consumption, so it's a very significant portion of our energy footprint. And when we talk about these chillers, the legacy technology has oil lubricated bearings, and that oil ends up in the refrigerant stream, which ends up coating your heat transfer pipes. Your heat transfer pipes are these very special dimpled pipes that have a very large surface area. So they put dimples in them to increase the surface area to increase the thermal conductivity. And the oil tends to coat those dimples and reduce your surface area, which impedes how much energy you can get, how much heat flow you can have through your heat exchanger. And so Trane, one of the larger HVAC manufacturers, did a study where they intentionally contaminated their refrigerant and observed how much efficiency loss they had as a function of oil being in their refrigerant. And they found, it ranged between about maybe 2 or 3% for a small amount of oil, and then you're up to 8% oil contamination. Suddenly you're at 15% of efficiency loss for your building. And if you're talking about a building that has, on order of a 1 megawatt system, this is a pretty significant concern. So they then went out to all their installations or several of their installations in the US, and they looked at how contaminated the refrigerant was. And they found that the lowest level of contamination of any installed unit was 5%, or 3.5%, which was a 5% reduction of efficiency. And the largest level was 23%, which you can see is off this chart for how much efficiency loss you have. So for this reason, all of the major HVAC manufacturers have added a product line that uses magnetic bearings to get rid of the necessity for oil lubricated bearings. So we've motivated it. This talk is about eliminating bearings. And how are we going to do that? With levitation? It's an April Fool's joke. Attempted. Okay, so not that kind of levitation. We're talking about magnetic levitation. And we're going to talk about 2 devices. The first device is an active magnetic bearing, and this is what people are more aware of. And the second device is going to be called a bearingless motor. So first, an active magnetic bearing is a distinct component of your motor system. So if you have, if you've got your motor, you can think about putting ball bearings on it or hydrodynamic bearings. In this case, we're removing those and we're putting a distinct device on either side that's used to support that shaft, to keep it centered. And this device looks an awful lot like a motor. It has a coil with stator slots. The difference is that you are making radial forces instead of torque. So it looks like a motor. It's controlled by power electronics, kind of like a motor is, but it creates radial forces instead of torque, or it creates axial forces to keep the shaft centered. And the advantages are pretty obvious. It's contact-free, so there's no friction, there's no need for lubrication. Kind of a caveat to it, and also a strength to it, is that you have to actively control this, which means you have a lot of sensors, and you can use those sensors for health monitoring. So you have to pay for the sensors, but you can also use them to extract more information about your system. You can detect when new vibrations develop and use that to determine the overall health of your motor. There's a lot of challenges, though. For one thing, these bearings are inherently have a very low force density, and they're very difficult to integrate. All these sensors have to be aligned very properly. If you don't get them aligned properly, you create a force in the wrong direction, and your shaft goes unstable and it crashes. You have a lot of wires. The reading material I gave you, I talked about going out and interviewing OEMs that integrate these systems into larger motor systems. And the #1 complaint that the OEMs always talk about is integration. I got all these dang wires. How am I going to connect them through? I need all these wiring harnesses. I got EMI issues, and so on and so forth. So the integration challenge, it sounds kind of mundane, but it really is a big pain point for this technology. And you can also have cross-coupling with your motor. So you can imagine that if your shaft or your motor becomes eccentric a little bit, suddenly there's a large unbalanced pull force that wants to bring it into the side. And your magnetic bearing is going to react to that and create a pull force the other direction to bring it back. And so if you're not careful, you can end up getting oscillations where the shaft vibrates back and forth. This is what this picture is showing. We have an orbit for our rotor that's not exactly, maybe it's too big, right? It depends on the size of your air gap. So that was a magnetic bearing. A bearingless motor, that's the second topic of today's talk. A bearingless motor is an electric motor that's able to produce both torque and radial or axial forces. So the idea is that this is not 2 distinct devices, it's one device that we're reusing the same steel, the same copper to create both torque and levitation forces. So it turns out that we can do this by modifying nearly any type of motor by simply adding another winding to the machine. So we're able to use the same magnetic field that's already there. We just add a small control magnetic field on top of it to create a radial force. And we'll be talking about exactly how that works and whatnot later in the talk. But first, let's talk a little bit more about why this is an interesting idea and how it can affect sustainability. So building off of the reading material, where I gave you some kind of motivating statistics, some eye-popping statistics for wastewater treatment, we can talk kind of more generally about a large industrial motor system that looks something like this. You've got the power grid directly connected to a motor. That motor is a very large motor, and it has a shaft supported by some kind of dedicated bearing lubrication system, and you've got these hydrodynamic bearings. The motor then connects through to a gearbox that steps the shaft speed up to a high-speed compressor and then goes to a throttle. And the only mechanism you have to control your power flows of the system is by opening and closing this throttle. So you can kind of liken this to your home, where you've got a faucet. If you turn that faucet, you control the flow rate out of your faucet by opening and closing a valve or a throttle, which is the knob on your sink. And if your water is pumped by this type of system, to a first order approximation, this system is drawing the same amount of power from the power grid, regardless of how much you've opened your faucet, regardless of how much water that you're actually getting into your sink. And so you can see that when you got your faucet all the way open, it'd be really efficient. When you got your faucet all the way closed, I mean, you got 0% efficiency, right? And so the Department of Energy has done studies on this and has shown that in large industrial motors over 20 horsepower, typically they're used in this kind of installation. And these systems consume up to 15% of our US electric energy and are wasting between 30 and 80% of that in throttles. So it's a pretty significant sustainability issue, right, or energy footprint issue, that we're consuming 15% of our energy and wasting between 30 and 80% of it in a throttle. And so there's an obvious solution to this, which is a variable speed motor drive. So the idea is, well, put some kind of circuit here that's able to spin your shaft at a variable speed, so that then you can control how much power the compressor is putting onto the fluid. And this is like a well understood and established solution. The thing is that for these very large motor systems, it's really not used right now. If you go and ask manufacturers of motors or users of these motors why they don't install the variable speed drives, they'll tell you, oh, they're too expensive, or they're too large, or they take up too much size and are run. Or the really big one is that they cause bearing degradation, they cause reliability issues in your motor. So these variable speed motor drives cause something called shaft voltage buildup. They've got EMI issues that causes a voltage to appear in your shaft, and this voltage will cause little arcs to appear to your bearings and cause the bearings to wear out and pit. And this is like a huge issue in wind turbines right now, but it's more broad. It's generally true of variable speed motor systems. They have this problem. So if we could only get rid of those bearings, then someone could use a variable speed drive and get rid of some of these losses. So I took that picture, and now we're shrinking down up here. We're going to talk about options to get rid of bearings with levitation. And the first option is a commercially available solution right now. You can go out and buy a motor that has magnetic bearings on it. And oftentimes what these systems will look like is since they got rid of the bearings, they'll operate their motor at a really high speed. And since motors, the output power of a motor is their torque times rotational speed, and the size of a motor is determined by the amount of torque it has to produce. When you increase your rotational speed, your size goes down. This is a very nice thing. If suddenly you don't have the speed limitations of this system and you can operate your motor at a really high speed, you can get the same power out of a much more compact system. So that's very, very nice. You can see that we trade off the mechanical complexity of this top system. We got rid of our gearbox because suddenly we're going to operate our motor at the same speed as our compressor, and we're also going to shrink our motor size down in the process. We got rid of the bearing lubrication system. So we got rid of the mechanical complexity, but now we've added electrical complexity. We've got these new actuators. We've got a variable speed motor drive to operate the motor. We've got a separate magnetic bearing controller to operate the magnetic bearings. And then, by the way, we better not let our shaft drop. So we need to have a battery backup system for the magnetic bearing controller in case the power grid flickers. So you have a battery backup system. So these types of systems have become popular in wastewater treatment facilities right now. Actually, the first installation in the US was in Green Bay, Wisconsin. And at that point, they did not use the battery backup system. So I had a fun conversation with the technicians at the facility, and he said, oh, the thing is great when it works, but within the first month, or I don't know how long, maybe the first year, the shaft had dropped a couple times. And they had a battery or not a battery backup, but a backup bearing system, which was like a loose fitting ball bearing that would catch the shaft. But that was only rated for so many drops. So if the shaft dropped maybe 3 times, then the system had to be taken down. It was out of commission until somebody could come in and replace the backup bearings. So this became a big problem because if you're treating wastewater, I mean, you don't really like to take your aeration equipment offline, or you're not treating sewage anymore. You have compliance issues. So in these systems, typically, the manufacturers will go to one supplier for the motor, another supplier for the variable speed drive, and a third supplier for the magnetic bearing controller. And it creates kind of an electrically complex system. So what I'm proposing in this talk and in my research is a more integrated solution. This idea of a bearingless motor that creates your magnetic bearing forces as well as your torque. And what we didn't mention on the previous slide is that bearingless motors do this in at least one direction that a magnetic bearing would support, which means you may need additional magnetic bearing support, for example, in the axial direction. We're going to talk about this more later in the talk. So in this system right here, I've drawn this with a bearingless motor supporting the shaft radially, and then having an axial magnetic bearing to support it axially. And because this is a very integrated system, it makes sense to integrate your power electronics into one unit. And then suddenly you don't need a battery backup system because your power electronics can detect when the power grid flickers and use the kinetic energy of the shaft of your motor to keep the thing levitated. So they can act like it's like regenerative braking in a car. You tap on the brakes and you're charging your battery. In this case, there's a big capacitor, and here you tap on the brakes of the shaft and you charge that capacitor up, and you can keep levitating until the shaft comes to 0 speed, then you're out of kinetic energy, and you can softly set your shaft down. So mechanically complex, electrically complex, and then minimizing electrical complexity. All right, so let's back up a second and talk big picture about magnetic levitation and what it's good at and what it's bad at. So one thing that it's not good at is force density. So if this is a normal contact bearing with a ball bearing, it can create a very high pressure on the bore of the bearing. It's got a very high force density. It's going to be compact relative to your shaft weight. Magnetic suspension, several orders of magnitude lower force density. But it's kind of comparison to these big oil bearings that we talked about for the large industrial motor systems. So anyway, the point here is that you're certainly not going to magnetic levitation to benefit from force density. So why would you go to magnetic levitation? It really only makes sense in applications where some combination of the following is highly valued. Friction-free operation, contact-free rotors, oil-free or lubrication-free systems, very long rotational life, variable rotor dynamics. One of the features of a magnetic bearing system is because it's active control, because you have a digital system controlling your actuators. You can change the stiffness and damping of your rotor, and you can change actually where the critical speeds appear in your rotor. Low vibration, and then this health monitoring idea. So right now, you can go and buy a set of magnetic bearings. These are examples of manufacturers that will sell you magnetic bearings or magnetic bearings plus a motor, or in Levitronics' case, they'll sell you a bearingless motor pump. We'll talk about Levitronics a little more later, but they make bearingless motor pumps for the semiconductor industry. So companies exist out there, mostly focused on magnetic bearings. And so if we take the 10,000-foot view of bearing technology today, we can say that right now, contact bearings and hydrodynamic bearings are fairly mature technologies. Magnetic bearings are a more recent technology that came on the scene in the 80s. 1985, I believe, was the very first installation of a magnetic bearing system in a compressor. I listed 1988 here because this was the first conference held specifically on magnetic bearings in the academic sense. And then they had a kind of a slow ramp rate, primarily due to their requirement for active feedback control and how complicated that was to implement with analog circuits and how expensive digital circuits were back in the 90s. And then more recently, in the 2000s, they've gained a lot of market penetration because of the low cost of embedded systems. Because suddenly you can do advanced tricks like self-commission a rotor by injecting a frequency and observing its performance with digital systems. Bearingless motors, on the other hand, really came on the scene around 2001, which is when Levitronics was founded. They were the first company to commercialize a brainless motor. They did this for an artificial heart. It was a left ventricle assist device. That's been a very successful thing for them. They sold it off to Thora Tech, and now Levitronics is focused on brainless motors for the semiconductor industry. And so right now, it's only been applied in rather niche places, not energy and sustainability type of applications where you think about energy footprint, but rather for really niche things where you really need the magnetic levitation and you really want the integration. So I put a question mark out here because the question is, what can brainless motors do in the future? And one of the things I'm going to argue in this talk is that we know what the issues are to make this have a meaningful impact in energy applications or high power applications, and people are starting to solve the challenges. So I personally believe it's going to look like this, but I'll let you make your own decision. So what I'm going to do with the rest of this talk, in the reading material, I gave you some background on the motivation for magnetic bearings and brainless motors, and we talked a little bit about this now too in terms of energy and sustainability. But I want to give you, I'm kind of a nerd, I want to give you some of the details of how it works, or at least take you under the hood of the car, so to speak, for a little while. And then we'll come back out and talk a little bit about how this impacts energy and sustainability at the very end. And so is there a cloud? Oh, there's a cloud over here. Okay, so I should wrap up by 4:20, is that right?
Yeah.
Okay. Okay, first, let's talk about a rotor. So if this is my rotor that I've got up on the whiteboard, and the degrees of freedom that we have to support in order to have it work in a motor system, there are 6 degrees of freedom. And look at my side, the first degree of freedom is our ability to rotate the rotor. So this is normal motor operation. Your motor will create a torque, and that's going to rotate your shaft. The second degree of freedom and third degree of freedom are radial displacement, like this, in the X and the Y direction. The fourth and fifth degrees of freedom are tilting about our X and our Y axes. And the final degree of freedom is axial deflection. So the idea is that in order to operate your shaft, you have to support all of these degrees of freedom. If you don't support one of the degrees of freedom, it's unstable. I guess the only exception to that would be rotation like this. If you don't support that rotation, that degree of freedom, you just don't rotate. But the other degrees of freedom, your shaft will fall down. And so I want you to keep that in mind as we go through these slides, because we're going to talk about different ways of supporting each of these degrees of freedom, whether it's with a bearingless motor, whether it's with a magnetic bearing, whether it's with passive magnetic forces. And to begin with, we're going to talk about simple magnetic bearings and how they work, and then build up on this to the bearingless motor. And so the world's most common magnetic bearing looks something like this. It's an 8-pole bearing. And you can think about it in terms of having 2 actuators, one actuator on the top, another actuator on the bottom. And so if you have this system, your top actuator and your bottom actuator each have separate coils, you can create forces that go by the square of the current in your coils. So it makes sense that if you excite a current up here, you're going to create a field that takes this path, and you're going to create a force in the upwards direction. You can calculate this force exactly using something called a Maxwell stress tensor, which is from your college physics course. We won't dwell on that too long. But the Maxwell stress tensor tells you that the force you create goes by the square of the magnitude of your magnetic field. So your magnetic field is created proportionally to your current, which means that your force goes by the square of your current. Okay, so great. We flow a current up here. We create a force that goes in the upwards direction by the square of our current. We create a current down here. We get a force going in the downwards direction by the square of our current. We can take the difference of these, and we have a force expression. And so this is very nice, except for it's kind of a pain because of that square term. We don't really like that square term. It's nonlinear. We like linear systems for control. So what we do is that we play a game where each current has a DC component and then a differential control component. And so what that means is that in my top coil, I'm carrying a DC current that's called capital IB, and I'm carrying that same current in my bottom coil. And if that's the end of the story, I create no net force because this expression says IB squared minus IB squared, and that's 0. But then to create the force, I add this IY term, which is positive in the top coil and negative in the bottom coil. And if you plug these expressions in up here, you end up getting this expression, which now is 2 times K times IB times IY And if you lump this into one term, you get a constant multiplied by IY, and that's a linear system. So that you can use superposition. You can recognize that if you change IY by 10%, your force is going to change by 10%. If you change IY by 50%, your force is going to change by 50%. And this is very nice. It unlocks our engineering toolbox for linear control. It makes us hardware engineers very happy. So, okay, how do you operate it? Well, you attach power electronics to each of these coils. This is just a single phase inverter. You control it to inject currents, and you're happy, you're levitating. And what does this look like from a control topology perspective? So you've got your shaft, you've got your actuator up here. Okay, you actually have a second actuator down here. We're just not going to show it. But you need to have some kind of sensor that detects your shaft's position. So you need to know whether your shaft is centered or not. And it takes that position, it compares it against a reference, which is where you want your shaft to sit. Presumably, your reference 0 means you want to sit in the center of your machine. You feed that into a position regulator, which gives you a command. It says, hey, I want you to create this much force. The shaft is eccentric, create this much force to bring it back to center. That force is converted into a current, which then goes to a current regulator that connects to the power electronics. So the current regulator tells the power electronics how much voltage to apply to that coil. Power electronics apply that voltage, and then voila, current starts to flow, which creates the force, and that is the feedback path for the system. So that was how a radial magnetic bearing works. The axial magnetic bearing is the same story, only now you're talking about creating forces along our axis, right? So if this is your motor shaft, the shaft has some kind of plate on it, and you've got a coil on either side of the plate, which is the same kind of actuator we talked about for the radial forces, and the same story repeats itself. You've got independent coil currents in each of these coils, which gives you the same force expression. You play the same trick with bias currents, and you get out the same force expression. So that's all very well and good. We can zoom back out a little bit and talk about advantages and disadvantages. As we mentioned before, you get this contact-free operation, you get a highly sensorized system that you can use for health monitoring, you can tune your rotor dynamics, and it's oil-free. But you're kind of stuck with this issue of a low force density, and that leads you to long axial lengths. And that is the major complaint of motor designers who have to use magnetic bearings, is that the things are so dang big. You can think about that being a problem from the perspective of like your raw floor space, but there's a subtlety here, which is that when you design a motor, you have to watch out for critical speeds. If your shaft length becomes too long, it starts to look like a flexible body. It'll actually start to arc, right? And motor designers want to stay away from those speeds. They want to keep their, you can say it two ways. They want to keep their shaft speed below where the shaft will start to deflect, or they want to keep their shaft short enough so that their design spec doesn't ask them to operate at the speed that would cause their shaft to start to become a flexible body. And so the magnetic bearings cause a problem because they add length to the shaft. Power electronics and sensors are expensive, bulky, difficult to integrate. Touchdown bearings are required, and you can end up cross-coupling with the motor. So, okay, so that's magnetic bearings in a very brief nutshell. Let's now talk about bearingless motors and how they compare. So again, the idea of the bearingless motor is that it's a single machine that is able to produce torque and magnetic bearing forces. And the goal is to replace one or more of those magnetic bearings, to eliminate one or more actuators from your system. And the basic story is that you use the magnetizing field of your motor. So if it's a permanent magnet motor, you use the permanent magnet field to replace that IB term we talked about, to replace that DC bias current. And so if you do that, you can leverage the motor's existing magnetic field without having to create this new bias field. And so it has the potential to solve some of the challenges of magnetic bearings. Fewer actuators, or in some cases no actuators, can really reduce costs. No actuators besides the bearingless motor. Better utilization of space, because you are leveraging the magnetic fields that are already in the motor, and the slots of the motor. You don't add extra components, axially removed from the motor section. So your motor is much more compact. And as we're going to talk about later, your motor typically is dimensioned to produce a power that that inherently lends it, if it's a bearingless motor, to be able to produce a force that's much greater than you would need. So you tap into the motor's inherent over-dimension in regards to the magnetic bearing forces, which further reduces your size. And we'll firm that up in a few slides. And it's a very integrated solution. So yeah. So let's give an example of motivating a bearingless motor and why it might be an interesting idea. So I've shown on this slide some hypothetical imaginary motor which has an air gap diameter, so that's our diameter across our rotor, of 50 millimeters. It's got a total rotor length going into the page of 50 millimeters. So this is a permanent magnet rotor. Here's a north pole, here's a south pole, and here's your stator with coils wound in the stator. And so this is a pretty, and we're assuming that there's the permanent magnet is sized to create a magnetic field in your air gap, which would be used to create torque. And this air gap field is a pretty typical field for a motor. And the first thing we do is we calculate, using that Maxwell stress tensor that we talked about, how much force is created on that rotor due to the magnetic field. So remember I said that the force goes by magnetic field squared. So we can use this constant 0.7 Tesla magnetic field and calculate the force that's created on our stator teeth or on our rotor. And we notice, well, of course, they're equal and opposite. We see a north pole here and a south pole there, so we have no net force. But we can talk about the localized force, and we can see that we're creating a 255 Newton force under each tooth. And we can compare this to the rate of the rotor, as described here. The rotor only weighs 7.3 newtons, so we can see that the motor, even though it's not a bearingless motor at this point, just the regular old motor is producing 35 times the rotor weight underneath each of its teeth already. And so the idea of the bearingless motor is, can we somehow disrupt the symmetry? Can we somehow make it so that you're not canceling your forces out to create a usable force? And so hypothetically, if we were able to do that, the next question is, well, how much do we have to disrupt this field in order to create our 7.3 newtons? And it turns out that we only have to add 5 millitesla and subtract 5 millitesla from the other pole in order to support the rotor weight. So you can see that already our motor has a very high capability of producing radial forces. It's just that we're not using it. And so the whole premise of the bearingless motor is, can we somehow disrupt the symmetry and use those forces? So there's different categories of bearingless motors, or you can create different categories of bearingless motors based upon how many degrees of freedom of the shaft they're supporting. And so if we go left to right, we can start with a 2-degree freedom bearingless motor. So in this case, you've got a motor that's able to produce radial forces, but that's it. So it's supporting 2 degrees of freedom, X and Y. And then the remaining degrees of freedom are supported by some kind of magnetic bearing. Or in the bottom case here, in this case, we're not going to talk about this too much, but the remaining degrees of freedom are actually supported by passive magnetic fields that inherently you have fields that kind of fringe from the top of your rotor over to the top of your stator. And so if you were to deflect this rotor down or up, those fields will tend to bring you back axially. And if you try to tilt the rotor, they'll tend to kind of bring you back tilt-wise. But of course, they're unstable in the radial direction, because if you move your rotor to the left a little bit, suddenly there's a large pull force that brings it in. It's like when you have your magnet close to a piece of iron, it wants to pull it up to the iron. Okay, so 2-degree freedom system, 4-degree freedom system. You can think of this as 2 bearingless motors, each able to produce radial forces. And if you do that in 2 planes, you can control tilt as well. And then an axial magnetic bearing to support the axial direction. And 5 degrees of freedom, where now your bearingless motor has got a cone-shaped air gap. And if it's got a cone-shaped air gap going in different directions, you can create axial forces as well as the radial forces. So it can support everything. 5 degrees of freedom for levitation, and the 6th degree of freedom would be the rotation. So this is the most integrated system. All right, so let's talk about how this works and how you can disrupt this symmetry. And we're going to talk about this in terms of a 4-pole motor. So up here I've drawn, this is our rotor, and we've got a north pole, a south pole, a north pole, and a south pole. And then outside the rotor, we've got a stator, which is where your coils would be. And it turns out that we can disrupt this symmetry if we create a new field in our motor that has plus or minus 2 poles. So this is a 4-pole motor. If we create a 2-pole field in the air gap, or a 6-pole field, we can create these forces. And I'm going to be talking about this occasionally in terms of pole pairs. And so if I say pole pairs, I mean a pair of north and south poles. So if this is a 4-pole rotor, it has 2 pole pairs. So let's start with just symmetry and how things cancel out. This is our Maxwell stress tensor calculations going by the square of our magnetic field. So if we graph what our magnetic field looks like as we go around the rotor, it looks like this. So that's starting right here, we see a north field, we see a positive magnetic field. As we go up 90 degrees, and then we have a south field, we go to 90 degrees, we have a south field, right? And 90 degrees, we have a north field again, and so on and so forth. So we can approximate this as being a sinusoid. And if we plug this sinusoid into this equation up here, we can get these localized force densities of red and the blue line. And if you integrate those force densities over the entire air gap periphery, you end up with no net force. So you can see that red is positive here, and it's equal and opposite on the other side. You have no net force in the x or the y direction. But now suddenly we've added a 2-pole field. So we put coils in this stator winding that create a field that takes this blue path. And we say it's 2 poles because everything over here looks like a north pole, and everything over here looks like a south pole. Then suddenly we can enhance the field of the magnets over here, and we're weakening it over here. And that's going to create a net force in the x direction. So if we, again, go back to our plot of the magnetic field in the air gap, and the black hashed line is our old field, and the blue line is our new field. So if we look on the right side, we see that there's a distance here, right? It's enhanced. And then going to the left side, it's marginally weakened. And, oh, here's the left side, it's weakened, right? And so now suddenly if we integrate our x line, we have a net force on the rotor. So at this point, what we've done is we've said, okay, we've got this coil installed in our stator, and if we inject a current, we can create a force in the x direction. So our only control is the amount of current we're injecting, and whether it's positive or negative, which means all we can do is create a force going like this. We're creating this force, we're not creating this force yet, right? And furthermore, if we start to rotate our rotor, you can see if we rotate 90 degrees, now this pole is over here and our forces switch directions. So what to do? We play the usual 3-phase trick, which is that we actually have 3-phase windings in our stator. Each are 120 degrees displaced. So now you can create 3 vectors that when you sum them up can be any arbitrary direction. So this looks like this is just a 3-phase motor winding. So you have one 3-phase motor winding for creating torque, and then you add this new winding for creating the levitation force. Okay, so at the end of the day, how does this behave? Well, we can model this as being a motor that has one winding for creating torque, and this is the normal, it behaves the normal way any motor would behave. We have a new winding that's used for creating suspension forces, and you have a mathematical relationship between the force vector that you create and the terminal currents that you flow into it. So if you solve that mathematical relationship, so right now we're saying if I have these are my currents, I multiply by this Ki quantity, now I've got a force vector. But what's useful to you is to say, hey, I need to create a force in this direction. What currents do I need? Well, you multiply it by K inverse, right? So this is a mathematical mapping between forces and currents. And it's reminiscent of what we said for the magnetic bearing. Magnetic bearing, we said F is equal to K times IY. Well, same thing, but now it's 3-phase systems, so you use some more complex math, but it ends up being the same physical thing. Okay, so right now, current bearingless motor technologies kind of stink. If you play this game, you really compromise on efficiency, cost, and power. And so the bottom line is that you must really, really need magnetic levitation in order to make this worthwhile. If you're taking a motor and you're compromising on efficiency, cost, and power, it's not a very good motor anymore. Those are like the 3 main things motors are supposed to do. So this has been successful in niche applications where you really, really need this magnetic levitation. And so one application we talked about is this artificial heart. And in that application, the need for magnetic levitation is very strong because if you use bearings, oil is not good in blood, and and also the point of contact with the bearing creates a pinch point where red blood cells get damaged. It causes thrombosis, and it actually is detrimental to the long-term care of the patient. So magnetic levitation, very important there, right? Also hygienic or corrosive environments where you need very high purity, the magnetic levitation becomes advantageous. But from an energy sustainability perspective, that's nice, it's great, but that's not what we're after. What I'm showing here is examples of the highest power bearingless motors that have been tested to date, and 30 kilowatts of this high has been published. And this is an efficiency of 82.7%, which, maybe on the surface, I mean, that's better than the 80% losses we were talking about. But it really isn't what you want to see for a magnetic bearing motor, for a motor that's using magnetic bearings. Most of these companies will tell you that they need something in the 96, 97% range. And 92.7% doesn't really get them excited. So okay, great. So why is it so hard to get to this high power level? And really, at least in my opinion, the big reason that I'm seeing in my lab is this decision to use separated windings, one winding for creating torque and one winding for creating levitation forces. And the reason is that you have to overdimension that levitation winding so you can also produce the worst case force. So if if somebody hits you with a forklift, or somebody's jackhammering next to your motor, you need to be able to create enough force so your shaft doesn't touch down. If you're spinning at 3,000 RPM, you've got this issue of if the shaft touches down, it's very, a major event, and it will wear out your backup bearings and make your system out of commission. So what ends up happening is you put a large winding in your slot space. So we've got a picture here. Here's a motor that's a bearingless motor. This portion of the slot, this portion of the coil is a coil that's used for creating torque, and this portion is a portion that's used for creating levitation forces. And you typically end up allocating between 25% to actually up to 50% of this whole space to that levitation winding, which decreases your motor power output by the same fraction. So you just gave up 25 to 50% of your power in order to make it a bearingless motor. And so, okay, well, the kind of obvious retort to that is, well, make the slots bigger. Use more slot space. What's wrong? Make your diameter a little bigger. Well, it turns out that if you do that, and this is especially painful when you go to high speeds where your diameters all come in, you end up with these really deep slots that cause your magnetic fields to take a long path, and that leads to large iron losses. It leads to a lot of fringing fields and leakage fields to the slot, and so it's got negative consequences for your motor performance. The bottom line is that adding the second winding is detrimental to your motor's motor operation, which is a hard sell for the energy sustainability applications. And also, it's non-standard to manufacture. Custom motors are expensive. If you're talking about high power motor systems, you're usually talking about price sensitive markets where you don't want to, a custom motor winding for a 1 megawatt machine is not great, right? Okay, so making this whole thing a sense of opportunity or a sense of like bittersweet resentment is that during normal operation, we find that when there's not a jackhammer next to your motor, when there's not an earthquake going on, you find that you really only end up needing about 2.5% of your slot space to support the shaft weight if it's a horizontal shaft machine. And you could be using 97.5% for motor current, except for you can't do that because you physically, you installed your conductors. You permanently put conductors in those slots, and those conductors tell you whether they're a motor conductor or a suspension conductor. And so we said only in emergency operation do we need this very high percent slot space for levitation forces, but we're kind of stuck with this breakdown no matter what because we permanently put our coils in there. And so one of the things that we're working on in my group is developing a combined winding, which is a single set of coils that can create levitation forces and torque. And so if you have a combined winding, then you can dynamically choose how much of your slot space is for levitation current versus torque. So you can dynamically, if you're using one coil, if all the conductors in here belong to a single coil, and you can, through some tricks, intelligently control that current in that coil to create either levitation forces or torque, then you can do both of these things. You can have the best of both worlds. And if during normal operation you only need 2.5% of your suspension current for levitation forces, then you haven't hardly derated your motor at all, right? It's a pretty good motor still. So this has been a focus area in recent times. There's a lot of literature on different approaches to doing that. We're taking one approach referred to as a no voltage combined winding, which I'll briefly highlight in a couple slides, and then we're going to skip to the conclusion. This no voltage combined winding is a technique where you have the same coils creating levitation forces and torque, but they're connected to separate terminals on the motor, so that one terminal only carries a torque current and another terminal only carries a suspension current. And you like this because your suspension power level is inherently very, very small. You want it to be because you want to be efficient, right? Compared to your motor power level. And so if you separate out the suspension and the motor current paths, it's it reduces the cost of your power electronics to operate your system. So there we go. So the idea is that you're trying to use one set of coils to create one field of a certain number of poles for torque. So if your rotor is 4 poles, you need 4 poles from your stator winding to be torque. And then using the same coils, you want to create a different number of poles for the levitation force. Because remember, we said it had to be plus or minus 1 pole pair. Or if you got a 4-pole motor, it needs to be 2 poles or 6 poles in order to create levitation force. So the question you should be asking right now is, how the heck can one winding create 2 fields? And being sensitive to time, we'll just go over this briefly. But the idea is, and I'm going to give a very simple example that's almost a trivial example for how this is possible. The idea is that if this is, here's a 4-pole permanent magnet machine again. So here's your north pole, south pole, north pole, south pole. And then in the stator slots, I've assigned a winding, sides, coils of a winding. That's a normal 3-phase winding. So this is a motor, it can create torque, that's great. And so if we look, here's a plot of the magnetic field created in the air gap from one phase of that winding. We can see we have a north pole, a south pole, a north pole, and a south pole. So it has 4 poles, which is the same as your rotor, so you can create torque, you're happy, that's good. Now we're going to take the same winding and we're going to reverse the current direction in half of the coils so that we get only a 2-pole field, which is used to create levitation forces. So if you compare between these 2 stators, you can see in slot 1, I've got 2 sides of phase U, 2 sides of phase U. Slot 2, 2 sides of phase W, 2 sides of phase W. But what I've done is I've reversed the current direction in half of those coils. And when I plot my magnetic field down below, suddenly I've got 2 poles instead of 4 poles. And if there's any highly motor-savvy person in the room, they're going to complain that, well, yeah, you're just canceling your current out in one of your slots. And that's true. In this case, this is a rather simple example that you'd say it has a poor winding factor for the levitation path. There's other example designs that don't have such poor winding factor, but this is a very nice illustrative example because you can clearly look at it and say, hey, there's 4 poles here, and suddenly we've got 2 poles here. So now the challenge is from your power electronics perspective is how to connect power electronics to these coils so that you've got 2 sets of terminals. One set of terminals, when you flow a current, creates this current direction, and the other set of terminals creates this current direction. And it turns out that there's a couple ways you can do it, and we'll just step through one of the ways. In this approach, each of these bridges is one of the phases of your motor winding. So you have 4 coil groups per phase in your winding, and you've got your motor inverter over here. So here's phase U, here's phase V, here's phase W. You've got a neutral in the center, and if you inject phase U torque current, I've got this right here, it's going to take a parallel path to the neutral point. This is a normal thing that's done in high-power machines all the time. You've got a parallel path to neutral. That's great. And in the center of this bridge is your suspension inverter, and you can see that if you inject a current from that, it's going to take the same direction as motor current in coil group D and coil group B, but it's going to be the opposite direction as the motor current in coil groups A and D. And so that's the magic of how you've created this second magnetic field. The second thing that's going on here is that we put dotted terminals on here, and that indicates the polarity of the back EMF in those coils. And by connecting the coils in this manner, the back EMF cancels out across the suspension inverter. So if I go from here to here, I see negative back EMF. From here to here, I see positive back EMF. So I see no back EMF across that suspension inverter. Whereas from my motor inverter perspective, I add the back EMF and add the back EMF. That's good. You want that, or you won't create torque. So there's another approach to this, and there's all kinds of fun considerations for how you design the machine and the power electronics to operate it. And just really quickly, I'll show you a picture of a prototype. This is something we've got in the basement of Engineering Hall. It's a magnetically levitated motor. So inside the stator housing, we've got 2 motor sections. Each section can create radial forces. So this is a vertical rotor, but you can control this direction of movement and then this direction of movement because you can create independent forces on the top and the bottom. And then we've got sensors that measure the rotor position. That's fed into a control circuit that we've designed that implements those control loops we talked about towards the beginning of the talk, sends out voltage references to a power electronic cabinet, which applies voltages to the motor terminals and makes the thing levitate. And right now we're working on designing, so this is kind of a proof of concept prototype for this approach to combine windings. Now we're working on thinking about higher power systems that give you benefit for large motors, right? So right now in our lab, it says 96% efficiency. Actually, we've got a mock design right now that's 97% efficiency, and we're hoping to build something this summer. And we're also working on, so the whole system, we've got the bearingless motor. We're also working on developing magnetic bearings that can create these radial and axial forces all within one actuator as well. So this combined winding bearingless motor has the potential to solve the challenges that you normally think about with magnetic bearings and bearingless motors by giving you this very dynamic ability to either create force or torque. So you can start to think about your machine truly in the sense of its ability to create a force density, whether it's a torque density or a force density on the rotor, and you can dynamically choose which direction or axis it's operating on. And so just some high-level thoughts for energy and sustainability. If you take the efficiency improvement that can be realized by adopting variable speed drives in the industrial sector, and you plug that in against the carbon footprint of generating electricity in the US, you can see that if we were to adopt, I think it's 80% of variable speed motor, of these large industrial motors to use variable speed drives, presumably using bearingless motors, we could, of course, decrease our energy footprint tremendously, but also single-handedly get to about 10% of our commitment for the Paris Agreement. So big footprint, significant. Yeah, okay, yeah, thank you. So what questions do you have?
I was wondering if you could say something about the applications of maglev in transportation. I think so far there's only one that's actually in working order. That's one in Wuppertal, Germany.
Oh no, there's a couple maglev lines. This summer I was lucky enough to get to go to a magnetic bearing conference in Beijing, and they took us on a maglev portion of their subway system, which is fun. I mean, it was kind of funny because like and this is what you want, but you wouldn't have known it was maglev, right? Like you're on it, everything goes smoothly, you get off it, and oh good, we were levitated, which is exactly what you want, of course, when you're riding on them. But there's no dramatic, oh here it goes up and off it goes. Yeah, so I'm not an expert on this kind of linear motion and magnetic levitation, but there's a lot of initiatives on that. I mean, Hyperloop, for example, in the US. And there's a few systems in the world about it. One of the challenges is that you have this very long track, and you're trying to actively control your machine along this long track. It can become very expensive. So a lot of the research focus is on developing technologies that keep the expense down. So put most of the active components within the train that's moving on it. The old systems, the legacy technology, it had the active components in the track. So on your whole length of track, you had coils that you're injecting current in and controlling, and that was where the cost came in.
I guess the classic example, though, is still the one in Wuppertal, isn't it?
Yeah, I tell you, this is outside of my expertise. Okay. I don't know much about that one.
Okay.
Yeah.
Is it like a huge multiple order of magnitude problem to go from something fairly stable like a stationary motor to a vehicle wheel where you've got a lot of off-axis?
Yeah. So mobile applications are interesting, are fun from a research perspective. But they're very challenging. So you have to deal with the frequency of the accelerations that you're exposed to. So if you put this in a car and you're driving on the road and you hit a pothole, you have to make sure that your magnetic levitation system is stiff enough to ride out that impact. And this is something that historically magnetic bearings have struggled with in a sense for a couple of reasons. But one of the reasons is you need to, that type of load is inherently very peaky, and so you need to overdimension your system enough to take that, which is going to be quite large compared to your shaft weight. And it's an area that I think bearingless motors have a lot of potential in, because you've got this inherent very high overdimension. If I'm only using 2.5% of my stator slot to support the shaft weight, I've got a lot of capability to overdimension that, right? I mean, it's inherently overdimensioned. Yeah, so I think that's a space that I think that we're going to see more movement in with improvements in brainless motors.
So like a hub motor would make a lot of sense for brainless.
Yeah, I don't know. I've been thinking a bit about electric turbochargers for vehicles. A hub motor makes me a little bit more nervous because I'm starting to think about the weight of the car and the unsprung mass. I don't know. I haven't done. It could be an interesting thing to work
Nobody
through.
likes unsprung mass.
Yeah. Nobody's working on that I'm aware of.
Yeah, okay.
Yeah.
These things you showed about coupling a magnetic bearing and bearingless motor in the schematic.
Yeah.
Is the efficiency affected by the type of load, whether it is a transient load, a variable thing? And also, the second question is, with all the variables involved, is there any way to have fault detection mechanism? And if there is a problem, do you correct it with a feedback loop by changing automatically the current, the amount of current in the windings, or? Right.
So so two questions here. The second question is fault detector. You're asking about fault tolerant machines. And so, yes, I mean, if you have this, I can rewind here, but you've got this three-phase system that can create 3 force vectors. That means that you've got redundancy built in. You actually only need 2 of these vectors to create any arbitrary direction force, right? Because they both have X and Y components in them. You can take away this ability to create force in this direction, and you're still able to levitate. Your force magnitude is reduced, but there's an ability to have some fault tolerance here. And this has become a research area. There's some publications on how control schemes to allow this to happen. And you're right. You have to adapt how you're creating currents, what the current path looks like, in order to maintain levitation. And can you remind me of the first question? Oh, I'm not answering. I'm supposed to be repeating the questions, aren't I? Well,
the load, depending on the load variation, if it's a transient load.
Oh yeah, right.
It's changing loads and the load coming back, and it's sort of maybe the covering the aspect of fatigue.
Right. So the question is about the load dependency of magnetic levitation or bearingless motor on its efficiency and its lifetime. And so, well, first of all, if I have a vertical shaft and I've got my shaft exactly centered, I'm at an equilibrium point, right? So I should actually need no energy to levitate it, which is kind of a joke because, of course, it's an unstable equilibrium point. If you tip off it, you're going to get pulled to the side. So the answer is, well, if you had this hypothetical situation and you're centered, you need no energy, then yes, inherently it's load dependent, because if I start pushing on it, well, now I need a current to bring me back, and so there's a loss. So you're right. There's a load. The types of loading you have in your system affects efficiency, certainly. The rule of thumb usually this is a very rough rule of thumb, but usually in a bearingless motor, the volt ampere requirement of your suspension electronics is about 1% of your power electronics for torque. And then the power factor is about 0.1. So you may need 1% of the power of the volt ampere rating of your motor, but then you have a low power factor in addition to that, so you end up drawing very little active power. But of course, if you're sitting here pushing on my shaft and I have to make a constant DC force to correct it, that's I squared R losses that appear in my rotor. That's just that appear in my motor. So my coil appears as a resistance. I've got a current going through it. I'm constantly fighting you, so there's a loss right there. The harder you push, the more current I have to flow, so the more losses there are. In terms of fatigue, this is going to come up mostly in the sense of starting and stopping, how frequently you start and stop your motor. It's usually not something we think about for motors because fatigue life ends up being so large, and the stop and start events are small. I'm sure a mechanical engineer might have more to say to you about that, but I'm an electrical engineer. I don't worry about such things. Other questions? Yeah.
Comments/questions. Obviously, it was good to see actually some of the companies who are playing in the sector up there as well. I think we can all agree it'd be nice to have much more energy efficient electric motors, that are quieter, cause less maintenance and all the rest of it, but there's so many different parties who care about those things, like reduction in greenhouse gases. If anyone cares, it's the national government, right? Or a large corporation trying to tag something. The user cares about the energy bill at the end of the month. The maintenance uptime, they care about that. But if the integrator, the manufacturer, like the OEM, who cares about the service contract, maintenance costs and so on. But where is this coming into the chain? Is this down at the manufacturer of the electric motor, who's a supplier to the integrator, who's a supplier to an engineering company?
Right.
And so, I don't think you've given it some thought around, okay, what's the application, the right insertion point for this technology?
So that's a very interesting question. I spent some time thinking about, so I thought about the wastewater aeration industry the most, and then HVAC some. And it was really eye-opening to interview. So in the wastewater treatment industry, it's like this. You've got the users of your systems are cities, municipalities. And so they've got a pump room at a sewage treatment plant. It's mandated as part of the Clean Water Act. You have to aerate wastewater as it comes through your facilities. It's called secondary treatment. You add oxygen to it. It helps the bacteria biodegrade the waste. And so the city has got this facility that houses, it's got a room in it, and it's got a bunch of motors connected to blowers, and it's all ducted out to tanks. Okay, so one level up above the city is a bunch of companies that rep other companies, that represent companies and will sell to the city, so distributors, right, or sales companies. And then a step above them is OEMs, and the OEMs typically don't actually make any components of the system themselves, or they make very few components. So if we go back here, so OEM, okay, there we go. So OEM will buy the motor from one company, they'll buy the main bearings from another company, the motor drive from a third company, and then they install it all in-house. So the motor, everybody cares about different things, you're absolutely right. And sometimes it's like contradictory incentives too. So the OEM, well, they will complain to you about integration issues with magnetic bearings right now. Or if they're doing this stuff up here, their customers are complaining to them about maintenance issues. So the OEM, in terms of this system, thinks about integration challenges and how dang expensive the components are, right? Your salesperson complains about how expensive this system is and is very worried about whether there might be a reliability issue with this compared to that. The city has multiple stakeholders. You've got political stakeholders who don't want to take risk on a system like this and have it blow up, right? Be in the pages of their local newspaper. But they also really care about the cost of operating it. And oftentimes, more than the cost of operating, they care about the initial capital cost, because if it's in their budget that year or it's not in their budget that year, a lot of times it has to be like a 1-year payoff, right? They have a certain fixed budget. If it fits, it fits. If it doesn't, well, sorry, it doesn't matter that you save this money going out long distance. We only had so much money available this year. The operators of the machines maybe care about, maybe they like that this machine required more maintenance because it keeps them employed, right? There's different incentives there. It maybe doesn't matter to them, the operators, that this machine was more efficient. The operators usually really like these machines from the noise and vibration perspective because they're so much quieter, it's an easier work environment, or they care about it in terms of how many of these systems they can fit in a room. So this is inherently smaller than this for the same power level, so they're happy that they don't have to expand their room, or they don't have to, it's easier to fit things in a nice, clean, tidy place. There's no oil leaking around, whereas this system is it can be kind of a mess, loud mess. So yes, there's lots of I don't know if I am really answering.
No, I mean, I guess it is just highlighting again, that's one of the challenges, is trying to figure out where to adoption, right?
And so I was interested in doing a startup company around this when I was a grad student. And it was kind of a chicken and egg game, because at least in the wastewater space, it was like, well, I needed like a pilot study to demonstrate it. But the city is not going to let me do a pilot study at their treatment facility, right? Yeah. Or the 10,000th one, maybe. Yeah. So HVAC is a challenging space. Not HVAC, wastewater aeration. I think HVAC is maybe a little bit more, you have a little bit higher of a pain point to the system because of the oil lubrication issue. causing efficiency degradation. And so that might be a more interesting place to get into. The challenge with it is that you're talking about higher power levels, and at higher power levels, everybody's more concerned about, explosions. So yeah, it's there's nuances for sure for how that actually makes it into commercial space.
Thank you so much for your time and your presentation today.
Yeah, thank you.